Hey everyone, so before we begin with our video, we would like to make a small request. Kindly subscribe to our channel and like the video if it helps you, and also share it with your friends who may benefit from the same. In this video, we'll be showing how you can maintain voltage and frequency through DQ voltage source inverter method. So first you'll need a universal bridge. And you'll have to convert it to IGBT diodes. So we'll double click on the universal bridge and we'll convert it to IGBT diode, and now we'll have to rotate the universal bridge. So now let's add a DC voltage source. So in this video we'll be using a DC voltage source, and we'll make a part 2 of this video where we'll connect a PV source. So we'll connect a DC source and we'll make it 800 volts for now. So since it's constant voltage, we will change this value of 800 in the future, and we'll show how the output voltage can still be maintained constant. So then next you'll need a PWM generator. So we'll choose a 2-level PWM generator. We'll connect the output of the PWM generator, which provides the pulses, to the gate terminal of the bridge, and you'll need a sine wave generator. So we'll take a sine wave generator. Actually, we won't be needing this sine wave generator. So let's take the sine wave and we'll keep the amplitude as 1, and we'll make the frequency 50 Hertz. And yeah, so the phase delay will actually be 0, and we'll set the sampling frequency to sampling time to T sampling. Now we'll need 3 of these. So I mean, each of them will have to be 120 degrees from the other. So we'll do the same. We'll keep the frequency as 50 Hertz, and we'll make the phase difference as minus 2 pi by 3. And for the other one, we'll make it plus 2 pi by 3. So once this is done, we'll need a bus selector which would aggregate the 3 signals. So we'll go and search for a mux. A mux will do. So we'll take a mux. And we'll need a go-to block. So we'll search for a go-to block. We can actually get the same by taking a from-to block as well. So we'll search for a from-to block. And we'll put this at uref of the PWM generator. And we'll name it as M, and we'll make it global as well for future references. And the output of this would go to the bus, the mux. So next we'll set the PWM parameters. We'll need to set the frequency, sampling time. So we'll name it as T sampling. Actually, you know what? We'll just name it as T, so that we avoid any sort of confusion later on. So we'll rename everything to T instead of T sampling. So now we'll need a power GUI block. So we'll make it discrete, and we'll again give it as T. So once this is done, we'll next we'll need a series RLC, series 3-phase RLC branch. So we'll take it and we'll name the inductance and resistance as RLF and LF. We'll need an RL circuit, we'll make it RL circuit. So you know what, we'll just actually make it R and L. And so in our other videos we've actually shown how an LC filter makes the wave sinusoidal. So this is the exact purpose for the RL and RC, which we will do now. We'll name it as, we'll give the value as 1 e power minus 5, and the capacitance we'll name it as 6. All these values will be I'll show you the formulas to all these values next. So once this is done, we'll short the other 3 terminals, which we will connect it to the ground. So next we'll need a 3-phase RLC load, but we'll make sure that the load is only resistive, so the value of inductance and capacitance is actually 0, and we'll have to set the phase-to-phase voltage and the frequency and make the inductive and capacitive part 0. So now we'll take a ground block and connect the RC branch to it. So once this is done, we'll need a 3-phase measurement block. Let's just drag and drop the 3-phase measurement block. Connect the terminals ABC to ABC, but before that we'll make it phase-to-phase measurement, and we will use labels. So let it be VABC, its default VABC, and for current it will be IABC. So click on OK. You can click on apply and OK, or you can just click on OK as well. So click on ABC and connect ABC as well. So now let's take a scope to realize the output. Let's make it a two layout scope output. So we'll have to give 2 inputs. We'll give current VABC as one input and IABC as the other input. So let's take a go to tag and from to tag and rename it as VABC and IABC. Now we'll come to the formula part. So as you noticed, we called in some places we named it as P, U, and P. So and C's and L's. So we'll define the formulas for all of them. Kindly take note of it. It'll be useful. So that's the formula for C, capacitance. So now we define the formula for L, and R will be 100 times L. So take note of these formulas. And run this code. So before you run it, you'll have to save the code as well. So I'll just save it as for parameters. And now let's run the program. I think there's an error, so we'll have to solve this error. The code still hasn't executed fully, so we'll have to find out what the error was. You can see it in the command window. So let's scroll down the command window. Yeah, as you can see, I've used an undefined variable p, so it's actually capital P. So just make sure you're careful about these things to avoid such mistakes. So once this is done, we'll go back to our simulation. Let's run the simulation. There's another, yeah, it's called R. Yes. So let's run the simulation, and yeah, so no errors in the simulation. So let's see the scoped output. So as you guys can see, it's within the boundaries of what we've defined, and it's a sinusoidal wave. So let's cancel this, and now let's come to the DQ part of the simulation. So you need a
get the DQ block.
As you can see, the inputs are A, B, C, and omega t. You'll also need a PLL block with this. The output of the PLL block is omega t. So let's give the ABC input. So voltage ABC input to the DQ block, and same for the PLL block. We'll have to set the parameters of the PLL block as well. The output of the PLL block serves as one of the inputs, omega t, for the DQ block, ABC to DQ block. And now let's check the parameters for the PLL block. We'll have to make it 50 Hertz, and of course the sampling time we'll have to mention it as t. Now we'll need a demux. Let's observe the peak value from the demux. So we'll connect a from to block and call it peak, and we'll connect this to a scope. Actually, even a display block would do. So we'll connect to a display block so we can see the value. So you guys can observe the value to be around 680 volts. So now we'll convert it to the RMS value. So we'll have to divide this value by 1 by square root of 2. So now coming to the control of the constant voltage part, we'll need a PID block, a discrete PID block. So taking a discrete PID block, we'll have to make it, let's give the time to be TSS. So we'll T into 100, and let's set the source to internal and proportionality value to 0.01 and integral value to 0.5. Click on the output saturation, make sure that the output value is 0.95 and the input value is 0.275. So what this basic does is it sets the value of the PWM within these two limits. So let's connect the output of this and we'll call it MA. So once this is done, you can take a multiplier block or a divide block, and we'll have to set the thing to multiply. So double click on the block and make it multiplication. One of the input terminals of the multiplier block would be MA, that is the output of the PID controller, and the input to the PID controller would actually be the peak go to from to tag. So we'll need an adder block, and let's make it plus and minus. So plus would be a constant value of 380 volts that we require, and the minus would be, as I had mentioned, the peak block, the peak block. So this should actually go to the minus. And now let's take a constant block. So let's give it the value of 380 that we desire. So we'll have to multiply 380 into square root of 2 as well, because it's with respect to the peak value, and peak is actually in terms of, it's in peak to peak and not in RMS. So it's 380 RMS into square root of 2, which will give you the peak value. So once this is done, we'll go ahead and simulate the model. So as you can see, the output value is close to 380 and it's plus or minus 5 volts. So that's it for this video, and you can actually, what else you could do is you could change the input voltage as well. So we'll just show that before closing things for this video. So we'll change the input voltage to 750 volts, and let's run it. And as you guys can see, even though the input voltage changes, the output voltage remains constant. So this is the way in which you could control the output voltage by DQ method of voltage source converter, where your converter is the inverter in this case. So you found this video useful. Kindly do check out our other videos and Like this video if it was useful, and subscribe to our channel, and do share it with your friends. Thank you.